Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is RET 120 Hydraulics. Okay, today we're going to have a discussion about velocity. So velocity, probably familiar with the term, akin to speed. Again, it's a unit of length divided by time. Just think about when you're driving your car, it's a mile per hour. Oftentimes velocity is expressed in many different units, namely feet per second, inches per second. But before we go into that, I want to talk about some pretty critical hydraulic topics related to velocity. And the first one is here, this concept. Pressure is quasi-equivalent to strength, and flow is quasi-equivalent to speed. And this is kind of a summary of what we learned in lab, our first lab. We had a demonstration of hydraulic power, and we're lifting something, and we also played around with the pressure relief valve. And one of the critical things you should be coming away from that lab with is if you adjust the pressure relief valve, you are adjusting the strength of the system, basically the ability of that system to produce force. If you are timing that cylinder, you're playing around the pressure relief valve in a number of different settings. Let's just say low, medium, and high settings. That cylinder will still extend at the same rate regardless of the pressure setting. Okay, so let's say we have a hydraulic system here, and it's being used to land dead whales, and we're going to put them on our ship and carve them up into soup or whatever you make out of a whale. And a whale is a pretty heavy item, obviously. So what's going to happen is you're going to adjust your pressure relief valve. Let's say it takes 900 psi to lift our whale onto our ship. If this pressure relief valve is set at 800 psi, the system cannot develop enough strength to lift our whale. And by the way, just here's a good exercise. Which position on our directional control valve lifts our whale? Well, it's the cross connect, because basically it's applying flow, pressurized flow from here through here into our rod end, and it's lifting our whale. Okay, so let's say again it takes 900 psi. We've got our pressure relief valve set at 800 psi. It's not going to lift the whale. Okay, it's just going to sit there. Now we go ahead and increase our pressure relief valve to 1000 psi, then it can lift the whale. Okay, and now the captain says, I want that whale lifted onto my ship faster. And then along comes Johnny Loco. He goes, well, I'm going to lift it faster by increasing the pressure relief valve to 1200 psi. And this is the point you got to stop Johnny Loco. Listen, you're going to walk the plank, because check it out. Adjusting that pressure relief valve will allow us to lift a bigger whale, but it's not going to get it aboard faster. Okay, so 1200 psi, yes, you can lift a larger weight, but it's going to lift at the same speed. The reason why is because speed is dependent upon flow. So as we remember, flow, to use a non-technical term, is the amount of stuff coming into a given area in a given time. Okay, so flow, let's see, amount of stuff, it's units of volume, typically expressed as a gallon, per unit time, typically a minute, or an SI, it's a liter per minute. And if you think about that, that's a gallon is 231 cubic inches. A minute is 60 seconds. So 1 gallon per minute is equivalent to 3.85 cubic inches per second. These are all the same, again, using our unit conversions. So it's the amount of stuff coming into the area in a given time. And if this cylinder has a certain volume, and you're sticking stuff into it at a certain rate, it's going to fill up, and fill up, thereby extending or retracting that rod. And now if you think about this as double the flow, you're basically filling that same volume, the cylinder hasn't changed, in a faster amount of time. Okay? So that means you have lifted this object or retracted or extended at a faster rate. Okay? So again, the critical concept to remember is pressure, increasing pressure for a hydraulic system will increase the force available for a given hydraulic system. We haven't changed sizes of cylinders or anything like that. And increasing the flow will increase the speed and conversely decrease the time it takes to do something. Okay. One of the other critical concepts, and it's not so critical right now because we're going to go back over this in chapter 6. We also introduce a device in here, and it was a flow control valve. Okay, and a flow control valve basically just limits the amount of flow to a known quantity. And for a cylinder of this orientation, we have a check valve bypass in our flow control valve. This is just kind of acting as a reminder right now. And the check valve bypass allows unrestricted flow in a certain direction. Okay, the problem is coming in this orientation when we want to drop our dead whale onto the deck. If there was no flow control valve with a check valve bypass here, and we put ourselves in the straight through condition where the rod end of the cylinder is now dumping to the tank at an incredibly low pressure, there's no pressure holding that. There's no back pressure there. There's no back pressure holding that object up, and the whale will just slam to the deck. So we want to go ahead and figure out a way to make sure we have controlled fluid flow in this direction. But again, we want to lift that whale as fast as we possibly can. So as much flow as our pump can produce, we want it to raise as fast as possible. Okay? So it stands to conjecture that our check valve would be oriented in this manner. So again, we're trying to raise this whale, i.e. retract the cylinder. As much flow as our pump can produce is going to get to this flow control valve, push that ball off its seat, and raise that as fast as possible. Let's say our pump is limited to 8 gallons per minute. All 8 gallons per minute, you're going to raise that whale as fast as possible. But now we want to go ahead and extend it. Let's say we've calculated out the required fluid flow that we want to gently land this bleeding pile of blubber on our deck is 2 gallons per minute. So what's happening here is pressurized flow enters the cap end and it's forcing fluid out of the rod end. It's coming this way. It cannot go through the check valve. It is forced to go through the flow control valve at a rate of 2 gallons per minute. Okay, so this is kind of a reminder of what we did in lab in our demonstration of hydraulic power lab. And don't worry, we're going to hit this thing again in chapter 6. What was I talking about? All right, we were talking about flow. Amount of stuff coming into an area in a given time, typically measured in some volume unit per unit of time. Most normally, gallons per minute. And as we showed, you can calculate cubic inches per second. Okay, typically flows from high to low pressure. And if we're going to use an electrical analogy, similar to conventional current flow, if an electron is just sitting there in a piece of wire and there's no potential difference across it, there's no electron flow. That's the same thing with fluid. If there's fluid in a hose and the pressure on one side is the same as the pressure on the other side of the hose, it's just going to sit there. But if there's pressure increase in one side and a lower pressure on the other, flow is going to move from high to low pressure, just like weather. A high pressure system and a low pressure system, basically wind is going to move in that same direction. Keeping with our electrical analogy, there's series and parallel flow paths. Okay, a simple series flow path. Let's say we've got flow entering this cap end and flow is leaving the rod end, but check this out. It's going straight into another cap end. And that one is forcing out of that rod end. That is a series flow path. Okay, so how do you think, and we're going to go back into examples on series and parallel cylinders in a little bit more detail, but think of how this thing reacts. If flow comes into cylinder A's cap end, there's cylinder B, simultaneously flow is coming out of the rod end of cylinder A, because that's the same device, that's the same piston face there that's moving. So pressurized flow enters cap end, leaves rod end, enters cap end of B simultaneously, and leaves rod end of B simultaneously. Basically, series cylinders are going to move simultaneously. Okay, and we're going to go into greater details. Think about travel length here. Think about just a little teaser here. Think the volume in here versus the volume in here. Which one's bigger? Which one's smaller? It depends. That's the answer. It depends, because you can size your cylinders appropriately or inappropriately. Parallel. A parallel path of flow. Think of parallel resistors. There's two flow paths. Think about this. Here's pressurized flow. It enters two cylinders, cap ends. Exits two cylinders, rod ends. So it's simultaneously entering the cap ends of cylinder A and B. And if it was a perfect world, they're perfectly loaded with the same weight and the exact same cylinder. They've got the exact same frictional coefficients. They would also extend simultaneously, because the deal is they have the same pressure requirements for extension. But now, think about this. Cylinder B is loaded with a larger weight. So pressurized flow enters the cap end of cylinder A and B, and pressure starts rising to 100, 200, 300. Let's say it takes 400 psi to move this guy. Cylinder A will extend until the limits of its travel have been reached. And then pressure will rise from 400 to 500 to 600 to 700. Let's say it takes 800 psi to move the load on B. Cylinder B would then extend. We'll go back into examples on series and parallel. Okay, one of the other things that we want to talk about regarding flow is the difference between laminar and turbulent flow. So laminar, to use a non-technical term, is smooth flow, turbulent, rough flow. And ideally, you want to have laminar flow. The reason why, basically, it's smooth movement in a straight path. This is characteristic of a properly sized passage and bend radius. Okay, so smooth movement, straight path, properly sized. We're going to come back into properly sizing and bend radius. Think about, here's the cross section of a pipe, and fluid is flowing in this thing. There's little friction along the wall here, so these things at these paths, these fluid where it's touching that, has a tendency to travel a little bit slower than the stuff in the center. But if it's a properly sized passageway, all this stuff is flowing in the same direction in a layered, smooth pattern, in a straight line. And this is in contrast to turbulent or rough flow. If you think about turbulent or rough flow, if you've ever seen a river in flood, Think about those boils and eddies and whirlpools. That's exactly what turbulent flow is. It's basically this rough flow, erratic flow that's occurring there. And the problem with turbulent flow is basically it's an inefficient use of your energy. It's basically energy is lost through that heat and friction. So turbulent is basically this rough flow. It's erratic, non-layered, in contrast to laminar, which is layered. Now think about the word laminar, laminate, layered, whereas turbulent is non-layered. Churning, that's a good word. This is characteristic of, let's talk about bend radius. In an ideal world, you've got enough hose and clearance to make this nice, smooth transition. What would happen if your hose was like this? Not so good. This is a nice, long, smooth pass versus this twisted passageway. Just think about all the possibilities to generate turbulence. So there is a certain bend radius given by manufacturers that you don't want to put a hose in that goes like this. Get a long enough hose. Go ahead and spend the extra money to get yourself a long enough hose to get that appropriate bend radius. And typically the bend radius is a function of the hose diameter. Let's say it's a 1-inch diameter, and let's say this particular manufacturer says minimum bend radius is 6D. So that means minimum is 6 inches. Okay? So that's the bend radius. Whereas this guy, look at this, those sharp turns. Look at the inside here, what happens. Let's say it is laminar flow right here. And again, it's smooth, straight flow. What happens when that straight flow hits there? It bounces off of here. And there's an eddy that's formed right here. This corner, these corners are incredibly, probably hot and noisy, So all that energy is lost in those particular areas. So again, keep your hoses properly sized and appropriate bend radius. We're going to go into sizing right now. Okay, so sizing a passageway. The analogy I like to use is a big crowded subway versus a trail. Now think about a subway. If the entranceway is properly sized, it's a large passageway versus a super narrow corridor. Think about this. Here's a properly designed subway passageway. And here's a subway passageway that is improperly sized. And let's say it's rush hour and there's 1,000 people per minute coming in to these two passageways. It's 1,000 people per minute that are being jammed in there, and it doesn't change. Okay, think about the people pushers in Japan. You've seen that. They've got the bar and they push people onto the subway. They're pushing 1,000 people per minute. That's a lot of people into these subway passageways. If it's a properly sized passageway, it can fit it. It can fit the amount of people, and they travel at a certain speed. If it's an improperly sized passageway, look at this. If it's 1,000 people per minute jammed into something of an incredibly small area, notice a dramatic pause, those same 1,000 people per minute have to move a lot faster in the narrow passageway versus this larger passageway. Okay? So now, that was rush hour, it's 1,000 people per minute. Now think of the middle of the night. It's not 1,000 people per minute. It's one coked up hobo per hour. It's a tiny amount of people that are coming into this same passageway. If there's just one hobo that's coming in to these passageways per hour, think of the flow, think of the speed through which this person travels. Incredibly slowly in this big passageway, and at a medium rate, appropriate rate for the narrow passageway. But now think about the expense for that. If your rate of travel, rate of people coming into this is 1 per hour, would you go to the expense of building such a large passageway? No, you'd probably build a narrow passageway. This is akin to resistors and wire sizes. Think of an incredibly thick wire versus an incredibly thin wire. This one's going to carry a lot more amperage versus this guy. But if you have a small amperage rate, why would you go to the expense of using this big wire? Just use this tiny wire. So basically, we're coming to a conclusion here. We're changing the flow rate and we're keeping the passageway the same. Okay, let me rephrase that. We've got a constant flow rate in two different passageways, one big, one small. The velocity has increased. Now we've decreased the flow rate, and the area, the big area, the velocity has decreased. Okay? So it's basically what I'm saying is everything is connected here. Okay? So there's an easy opportunity to get lost in the death by formula approach. And you're going to see in your book V is equal to L2 times area times L1 divided by 231, times 60 times flow rate Q. Don't do this. This is dumb. Because you're never going to remember that. You're not going to remember it. That I love my students, but there's two people that kind of drive me crazy. The first one is Joe Slacker, who doesn't read, doesn't show up to lecture, doesn't show up to lab, and he blames the water for drowning him when he's not kicking his legs. And the other student that kind of drives me nutty is the Little Miss formula that knows every single formula, and that's all she knows is the formulas. And if she gets in a situation where she doesn't have a formula memorized, she goes darn and just can't figure it out. Okay, and basically the problem is with both these students, they both understand nothing about the subject we're talking about. All this person knows is just a formula. And how I get around this formula block here, I don't like using formulas. Think of the concepts that we just talked about here, about varying the sizes of passageways, varying the amount of material entering it. And just think in those concepts, and you can honestly derive any formula. And in this particular case, we're going to look at velocity, which is the speed of something. And I'm going to put something up here, QVA. And notice how I've put it in that triangle formula, which we're incredibly familiar with. Okay? And then I'm going to draw two circles. This one has a 1-inch diameter. This one has a 1-inch radius, which we all know means it has a 2-inch diameter. Look at the relative sizes of these two circles. And if you think about it, the area here could kind of be shoved into this spot. So I've doubled that diameter. What has the area done? It's increased 4 times. Okay, and do the math. Trust me. Let's go back to our passageway analogy here. I've got a narrow passageway versus a passageway 4 times the area. Basically, for the same flow rate, 5 gallons per minute, it will have to move a lot faster to get through that pipe versus this pipe, because there is 4 times as much area, 4 times as much space for that fluid to spread out and go through that same passageway. Okay? So let's go back to our little triangle thing here. And now use this concept, and this is my point about the whole death by formulas. Don't do death by formulas. Don't be Little Miss Formula or Little Mr. Formula. I want you to have a conceptual understanding of this. Use this conceptual relationship and account for units. And that is kind of where you need to start doing some thinking. Okay, so let's just use our conceptual relationship here. Q, if we want to solve for Q, what do? We take the velocity times the area. And now think about that. If our flow is our velocity times our area, think about this. If our velocity stays the same, 12 inches per second, 12 inches per second, 1 foot per second, and our area doubles. Now I'm talking, trying to, so 1x, 2x. I have not doubled the diameter. In this case, I've doubled the area. Except for, remember, doubling diameter increases area 4 times. I've doubled the area. That means if that same velocity and I've doubled the area, I've increased my flow. So now velocity. Think about velocity. Flow divided by area. So if the flow rate stays the same and my area decreases, what happens to velocity? Flow rate stays the same, area goes down, it's a smaller number on the bottom, and this one stays constant up top. What happens to V? V increases, okay? Again, passageway. So I've gone from big area to small area, same flow rate, still 1,000 people per minute. Again, velocity increases to get that same amount of people per minute to go through that narrow passageway. Conversely, I increase the area. So keep flow rate the same, increase the area. Velocity decreases. Now you can take a leisurely time going down that hallway and looking at all the artwork. Okay? Talk about this. Area, QV. So, 4, basically increasing velocity. Let's say we've got a means of measuring the speed of that fluid in that particular passageway. If we notice an increase, let's say we've got a constant flow rate, it's an incredibly fast velocity, well, we can conjecture that we have a very small area. Okay, so if this is an incredibly large number, we would expect that to be a small area, an indication of an improperly sized pipe. Okay, because there is certain limits based on manufacturer specifications. You want to keep flow rate to, you want to keep velocity to a certain feet per second. Okay, so and now, so conceptually, that's a pretty easy exercise, the QVA triangle, and I had a lot of lead up to it, but it just helps people understand, I've doubled my velocity and kept the area the same. What's happening there? Well, chances are your flow rate has increased, okay? You're moving more material because it's going faster through the same area. All right, let's just do a simple example of this. And the example is, yeah, it's using QVA triangle. Now we got to start accounting for the units. Okay, let's say we've got a flow rate of 5 gallons per minute. And it's going through, let's see, an area, yeah, just a 1-inch pipe. 1-inch internal diameter pipe, IDE pipe. What's the velocity in feet per second? Okay, so 5 gallons per minute is crowding through that particular area. We've got to figure out what velocity is. So velocity, flow rate divided by area, and figure out the area. Pi over 4 d squared, 0.7854 inches squared. 5 divided by 0.7854 inches squared, gallons per minute. And that answer will be wrong. And the reason why it's wrong is because we have not accounted for units. Think of it this way. A gallon per minute is 231 cubic inches per 60 seconds. And this is going to give us 0.7854 inches squared. That inches squared crosses out, and we're left with an inch per second. We've got a unit of length per second, which gives us 24.51 inches per second. But let's say we wanted our answer in feet per second. That is not an appropriate unit. We want 24.51 inches per second. What is a foot? A foot is 12 inches per foot. Inches crosses out. 2.042 feet per second. Makes sense. Now let's just go ahead and just do a simple confirmation of some of the concepts we talked about here. Okay, so that was a flow rate of 5 gallons per minute through a pipe of 1-inch internal diameter. What would happen to the velocity of this same system if it was a 2-inch pipe? So now here's a 2-inch pipe. And you shouldn't even have to do any single calculations at all. Just first off, tell me if it increases or decreases. Does the fluid velocity increase or decrease? It's pretty simple. The answer is decreases. The reason why is because it's still 5 gallons per minute. Going through, in this case, something with 4 times as much area because the diameter has doubled. Okay, how much does the velocity decrease? Well, it decreases by a factor of 4, and just run the numbers. Okay, 5 gallons per minute, still again 231 cubic inches per 60 seconds. What's our area? Well, the area of pi over 4, 2 squared. This number over there, it's 4 times as much as that. It's going to give us 6.13 inches per second, which if we do correctly our conversion, 0.51 feet per second. Basically, it's only a quarter as fast as it was previously. Okay? All right, go back to the first system we worked at, where it's 5 gallons per minute, inch internal diameter pipe, and let's say flow rate doubles to 10 gallons per minute. Does the velocity increase or decrease? Pretty easy. It increases. How much does it increase? in this particular case, it's going to be twice as fast because twice as much stuff is going into it. So basically just replace our 5s with 10s, and ultimately you're going to get roughly 4.08 feet per second. Okay, just use the concepts. Don't worry so much about formulas. Use the concepts and account for units. So what device do we use to measure flow? Measure flow, flow meter. Okay, so a flow meter schematic symbol, it's like this, often has a direction of flow indicated on it. And again, that direction of flow is pretty critical. This is what some of them look like here. It's basically got a little sight glass in there that you can see. Well, basically it's a sight glass with a calibrated weight in the center, and that calibrated weight has got a pointer on it, and it slides up and down that scale, and that pointer is indicating what the flow rate is: 5 gallons per minute, 4 gallons per minute. Okay, typically they are mounted vertically, and obviously the correct orientation. Okay, the reason why is because the flow rate, as it's the preferred orientation, is pointing, let's say in this example, is up. It is pushing against that calibrated weight. It's lifting it up to a certain amount. And if it's mounted in any other orientation, you're just not going to be able to read it. Okay. There is also digital versions of these things, and a digital version is pretty neat because it's taking this data, and it could also be recording it, not only displaying it. These manual visual ones, they're just displaying it and you got to look at it. A digital flow meter is actually taking the data and maybe recording it, maybe sending it to another portion of the system, and you can make decisions off of the flow rates. Okay, so again, let's go back to the most critical thing I talked about today. Flow is indicative of speed. Okay, pressure is strength. Increase the pressure, you can increase the force available to a system, increase the flow rate, and increase the speed at which that system activates. They're two independent variables for a system. Okay, so the other thing I wanted to talk about was, again, is our laminar and turbulent flow, proper bend radius and sizing, and velocity. Okay, so flow is related to velocity through this conceptual relationship of QVA. And again, you got to remember to account for units and do not formula me to death or yourself to death. And that's what a flow meter looks like. Okay, we're going to continue on with some more properties of hydraulic fluids.